Hello. In this video, we will look at polynomial functions of higher degree. You will study basic features of the graphs of polynomial functions. One feature is that the graph of a polynomial function is continuous. So if we look at the picture, you will see a nice flowing graph. So if we look at the picture of these two graphs that I have, you will notice that on the first picture, on picture A, okay, the graph is continuous. Okay, there is no gaps in the graph. These two functions here are continuous. Well, this function A is continuous. If you look at picture B, you will notice that in picture B, there is a break. Okay, this graph has a gap or a break. Okay, so then this is not continuous. This is not continuous. Okay, therefore, this is not a polynomial function. So by looking at the pictures, by looking at the graph, you're able to identify if it is a polynomial or not. Okay, that's just the basic of the graph. Another feature you will see is that polynomial functions are very smooth, meaning that they're rounded terms. So let me show you a picture of that. So if we look at these two graphs, okay, you will notice that in the first graph, which we call A, the turns here are very smooth. They're sort of rounded turns, okay? And that's why we mean that they're rounded turns. If you look at picture B, okay, you will notice that this turn here is very short. It's not a nice rounded turns or turn. Therefore, you can say that graph B is not a polynomial function. You will notice as you sketch graph of polynomial functions of degree greater than 2 is oftenly more involved than sketching graph of polynomial functions of degree 0, 1, or 2. However, using the same features that you have used when you had a linear function, the table, that method will also work to plot a function. So we'll see in a few minutes how, by using the table method, we can get a graph. However, that method is very lengthy. So it will help us if we understand some of the characteristics of the polynomial functions. So polynomial functions that have the simplest graph are monomial function. And remember, a monomial function is a one-term polynomial, okay? So x to some power n, right, where n is an integer greater than 0, will be the simplest polynomial function, okay? Now we'll see that when n is even, okay, when n is even, the graph is similar to the graph of x squared. So we will see here that when n is even, okay, our graph is similar to g of x or f of x equals x squared. Okay? And when n is odd, the graph is similar to h of x equals x cubed. So let me just show you two pictures of that. So you will see here in picture A, okay, the light color graph is x squared, okay, and the dark color graph, okay, so this is x squared. Remember, it is continuous, okay, and the dark color graph is x to the fourth, okay. So notice that they're very similar in shape. They are parabolic, okay, they are parabolic. On the other hand, if you look at the cubic graph, x cubed, which is the light color graph, okay, and notice that they do intersect at some point, and the graph x to the fifth, they look very similar. Okay? So any graph with an even degree, okay, or an even power, so even n is even, okay, power, or even degree. So we usually call the power and degree has the same meaning, okay? We say that the power is even or the degree is even. And then on here, you will see that n is odd, okay? Odd power or odd degree, okay? This here is an or. So anytime n is even, you will have a graph that looks like that shown in picture A. And anytime it is odd, you will have graph that looks like that of picture B. So if we're asked to sketch the graph of minus x squared, okay? So one of the things we can do this by creating a table. So we can graph by creating a table of values. Now you have to be careful because whilst creating a table of values, remember these graphs are not linear. So you will have to create a lot of points. So if we create x and then f of x, so if we create minus 4, minus 3, minus 2, minus 1, 0, okay, 1, 2, 3, and so on, you will notice that f of minus 4 will be minus 4 squared, which is equal to 16. Okay, f of minus 3, we have a minus x squared. Okay, we have a minus x squared. So this becomes minus and then minus 4 squared, okay, which becomes minus 16. Yeah. So this becomes minus a minus 3, which becomes minus 9. And if you continue to do this, f of minus 2, this will be equal to negative 4. F of minus 1, this will be equal to negative 1. F of 0 will be 0. F of 1 will be minus 1. Okay. F of 2 will be minus 4. F of 3 will be equal to minus 9. And if we plot these points, on the graph, okay, on the xy axis, you will observe that you will have a graph that looks very similar to x squared, but there is one little difference. Yeah, there is a little difference. You will see that this graph is not pointing upward, it is pointing downward. Okay, it is pointing downward. Okay? Here is the point 0, 0. And this is the function f of x equals minus x squared. F of x equals minus x squared. And when the graph, when these arrows are pointing down, okay, we say that this is concave down. We know that because the arrows are pointing down, okay? When the arrows are pointing up, okay, when the arrows are pointing up, we call them concave down, concave up, okay? So now let's look at the graph of x plus 1 squared. Now keep in mind here, the degree is still even, okay? So you can create a table for this graph also, okay? You can also create a table for this. Now, x plus 1 squared will be very similar to x squared, okay? So by creating a table, and I will let you create the table on your own, I will just draw the difference in the graph so you can see what's happening here, okay? You know that if you sketch the graph of x squared would look like this, okay? This is the graph x squared, okay? But if you have x squared plus 1, if you have x squared plus 1, what will happen is that when you sketch this graph, I'm going to put minus 1 all the way out here. Okay. You will notice that your graph will now look like this. Okay. And this is the graph h of x equals, let's write it above here, h of x equals x plus 1 squared. Okay. So later on, we will see that this point here has transformed to there. And that is called transformation of functions, right? Transformation of functions. So it's very similar to x squared, just that the function has moved to the left by 1 unit. So how about if we have to graph the function now, g of x equals x plus 1 to the 4th power. So note, okay, note, degree is even, right? 4 is even, okay? So the graph is similar to that of x squared, okay? The graph is similar to that of x squared. And you will notice that if you create a table of values for this graph, okay? If you create a table of values for this graph, you will see, okay, that this graph is also moved 1 unit over to the left. Okay, also move 1 unit over to the left. And if you graph this, okay, if you graph this, our graph would look very similar to this. And this is the graph g of x equals x plus 1 to the 4th. So what you should do here is make sure, create a table, right? you can create a table of values. Now, what is very important for you is that to see that the coefficient, which we call the leading coefficient, has a very important role of these graphs. So let's look at the leading coefficients now, okay? Leading coefficients. So what do we mean by the leading coefficient? Now, if I give you f of x is equal to x squared, the leading coefficient here is 1. This here is the leading coefficient. Okay? If I tell you g of x is equal to 3x to the fifth, this here is my leading coefficient. Okay, so the leading coefficient is that number. Okay, it is the number in the polynomial with the highest degree. So this is the number in the polynomial with the term of highest degree. Okay, and what do I mean by that? For example, if we have, let's choose a different, h of x is equal to 3x squared minus 6x cubed plus 7x to the fifth. Okay, what we have to do is to rewrite, and if we rewrite this, we have h of x is equal to 7x to the fifth minus 6x cubed plus 3x squared. So therefore, the leading coefficient is 7. Okay, this is our leading coefficient. Now, the leading coefficient has a very important role. Okay, has a very important role of the shape of the graph. Okay, so now we can look at what is called the leading coefficient test. Okay, let's look at the leading coefficient test. So what we'll see in the leading coefficient is that the graph either rise or fall without bounds as x move to the left or to the right. So the leading coefficient will show the end point behavior. Okay? It will show you the endpoint behavior. So if you look at the picture here, notice that this here, when we talk about the endpoint behavior, we're talking about this part of the graph. Okay. And you will notice that if the leading coefficient is positive, okay, the graph will always fall to the left and rise to the right. Anytime. Okay, anytime the leading coefficient is positive. In addition, here we're talking about an n degree where n is odd. So two things to note here, okay? Two things to note. We will notice that in this case, yeah, that the leading coefficient is positive. Okay? Is positive and the degree is odd. Okay. On the other hand, on the other picture, okay, so that's for this graph here. Okay. You will notice that if the leading coefficient is negative, okay, and the degree is odd. So notice that when the leading coefficient is negative, okay, the graph sort of like flips. It rises to the left, okay, rise to the left, falls to the right. It rises to the left and falls to the right. So the leading coefficient really helps to visualize what's happening. Now, when we talk about this, there's a mathematical way of writing it, okay, which you should be aware of. So when we say a graph falls to the left, okay, when we say a graph falls to the left, okay, what we're saying is that as x approaches negative infinity, falls to the left, okay, the left side. This is the left side, okay. The function f of x approaches minus infinity, okay. So this here is the graph. This is the left side of the x-axis, okay, the graph of the function. Okay. So this is the way we write it, okay. This is just the notation in which we write. Now, similarly, what happens when n is even? Okay? When n is even, we already know that the graph is parabolic, right? And what happens now to the leading coefficient? How does that influence the graph? So here again we have two pictures, okay? Here again we have two pictures. And notice that when n here is even, okay, and the leading coefficient is positive, the graph rises to the left and to the right, okay? So you should note, okay, observe or note when the degree is even, okay, regardless of the leading coefficient, both sides of the graph, or both ends if you want to say, always points in the same direction. Always point in the same direction. And also note when the degree is odd regardless of the leading coefficient, regardless of the leading coefficient, the graph, okay, points in opposite direction, opposite direction. Okay. So you will see that if you compare the two pictures, if you compare any family of x square, okay, if you have x square, you will notice that both ends point in the same, we don't even need the axis. Both ends will point in the same direction, okay? Here we have same direction, okay? If we have x cube, okay, x cube, one end is pointing up, here goes up, here goes down, okay? Different direction. This will always be the case, always. So this is something that anytime you see odd degree, you already know what's happening. Anytime you see an even degree, you already know what's happening with the endpoint behavior. Yeah, the endpoint behavior. So if I give you an example now, if I give you an example, okay. So example, describe the endpoint behavior of the function, okay, f of x equals minus x cubed plus 4x. Now to do this, okay, so to do this, we must identify the leading coefficient and the degree. Okay, so notice that the degree is 3, odd. Okay, notice that the leading coefficient is negative. Yeah, it is negative. So this tells me, okay, since the degree is odd, the graph or the end of the graph will travel in opposite direction. Okay, so this is 1. And 2, because since the leading coefficient is negative, if it is negative, the graph will rise on the left side. On the left side. Now, how do I know this, right? How do you notice? So you should want to remember, okay? So remember x cubed falls to the left. So minus x cubed will rise to the left. So if you have x cubed looks like this. Okay, here we fall, here we rise. Minus x cubed looks like this. Here we rise, here we fall. Okay, so we can say, when I ask for degree, we can say the degree is odd, the leading coefficient is negative. So the graph, so this graph, and we're talking about the graph minus x cubed plus 4x will rise to the left and, okay, falls to the right. Okay. We don't care, for now, we don't care about the plus 4x. Later, when we start to graph this in detail, we'll pay more detailed attention. Another way of write this, we can write this as follows. And this is something that I strongly recommend. As x approaches minus infinity, okay, did we give our function a name? F of x, because this was f of x here, f of x approaches negative infinity. Okay, and now we do, so this is the left side. Now we do the right side. As x approaches positive infinity, f of x will also approach, did I do that right? Minus x cubed on the left side. Yes, it goes towards positive infinity. Why did I say that? We did say that the graph will rise to the left, right? The graph will rise to the left. If it's rising to the left, it goes to infinity. Okay. And on the right side, it falls. So this goes to minus infinity. This is the right side. I want to make sure we get that correct. So it falls to the right. Falls to the right, goes to minus infinity. So you can really tell a lot by looking at the graph. You can tell a lot just by looking at the equation. Let's look at another example. Okay, example. Let's describe the endpoint behavior of h of x equals now x to the fourth minus 5x squared plus 4. Okay, so very similar what we did above here, right? We'll identify the leading coefficient and the degree. So let us identify the degree and the leading coefficient. Okay, so here we have the degree is 4 even. Okay, and 2, the leading coefficient is positive. Okay. So that means, this suggests that the graph will be similar, or that the endpoint of the graph end point of the graph will be similar to x squared, okay, or 1x squared if we want to be more detailed. Okay, so we don't care right now. We ignore, we only look at the first term. That's all we're looking at. So what we can say is that the graph of h of x will rise to the left, okay, and rise to the right. Okay. Or we can say as x approaches negative infinity, h of x approaches positive infinity. Okay. This is the left side. And then we can also say as x approaches positive infinity, h of x will approach positive infinity. This is the right side. So just by looking at the bleeding coefficient and the degree, you can tell the behavior of the ends. Now, another feature that will help us is if we find the zeros of the polynomial or the intercepts of the polynomial. Yeah. So it is possible to show that for a polynomial function of degree n, yeah, we can say that the function f has at most n real solutions. So let's look at that. Let's look at the zeros of the polynomial. Okay. Real zeros. So a polynomial function, okay, which is f, we call it f, of degree n, okay, has at most, okay, n real solutions or n real zeros. Zeros is the same as the solution, okay? We can also say, in addition, we can say that the polynomial function f has at most n minus 1 turning points. And please note that a turning point is what we call a relative minimum or a relative maximum. Okay, so turning points is a relative minimum or a relative maximum. Okay, relative minimum or relative maximum. So those are the things we will look at now. So we can say that when f is a polynomial function and a is a real number, these statements below are equivalent. X equal a is a zero of the polynomial function. Okay? X equal a is a solution. So you will notice that 0 and a solution is the same thing. Okay. So let's look at this because this is just new terminology to you. For example, okay, example, given f of x equals x squared plus 7x plus 12. Okay, if I ask you to find 0, okay, this is the same as finding the solutions. So x squared plus 7x plus 12 equal to 0. So x plus 3 times x plus 4 is equal to 0. So there we have x plus 3 is equal to 0, or x plus 4 is equal to 0. So x is equal to minus 3, or x is equal to minus 4. These are the zeros. Okay, these are your zeros. So x equal a is a 0 of the function. Okay, so in this case, my a is minus 3 and my a is minus 4. Now, x equal a, this is also called the zeros or solutions. Okay? Now, x minus a is a factor. These things here, these are called the factors. Okay? These are called the factors. Okay? From the factors, we get the 0. Now, the x-intercept is, okay, minus 3 comma 0. Recall x-intercept let y equal 0 and minus 4 comma 0. So we have two x-intercepts here. Okay, we have two x-intercepts. So you're familiar with this, is just that the terminology, these are new words. Okay, zeros, okay, zeros, new word for you. Okay, so pay attention to these new words. We also have what is called a repeated 0. Okay, so, and we talk about this when we talk about multiplicity. Okay, we talk about this when we talk about multiplicity. So what does this really mean? It means that if we have a polynomial, okay, let's look at a polynomial f of x is equal to x squared plus 6x plus 9. Okay. Now, if you factor this, if we factor this, we have x plus 3 times x plus 3, which is the same as x plus 3 squared. Yeah. So we'll see that if this power here, okay, and it has to be greater than 1, if that power is even, the graph touches the x-axis. Okay. It touches it, but it does not cross it. And when that power is odd, the graph crosses the x-axis. So let's make a note of that. Let's make a note of that. So notice here that k in this case is, in my example, k is equal to 2. Okay. So when k is odd, the graph crosses the x-axis. When k is even, the graph touches but does not cross. Okay. Those are things we'll be looking at. So what we're doing here, we're looking for little hints, so we can become very proficient at graphing polynomial functions, very proficient. So by finding the x-intercept or the zeros, by looking at the endpoint behavior, we already know how the graph will look at the endpoint. So let's look briefly at the intermediate value theorem also. This is another theorem that will help you. And basically what it's saying is that if you look at two values on the graph, okay, or 2 points on the graph of a polynomial, and the y values are not the same, then there is some x value that falls between those two y values. So let's look at this from a graphical perspective, and we will talk about this more in detail later. So here's a picture that you will probably get this more from. So if we have two x values, a and b, okay, these are two x values, a and b, okay, where a is less than b, okay. If f is a polynomial function where the y values are not the same, then in that interval ab, okay, the function has some value between f of a and f of b. So let's look at that from losing some numbers, okay. If we have a graph, and we'll look at the cubic graph, okay. If we look at the cubic, where we know that 1 is a point on the graph, 2 cubed, 2 times 2 is 4, 4 times 2 is 8. So 1, 2, so I wouldn't have enough room here. So let's not make this 1, 1. Let's call this 1, 2, 3, 4, 5, 6, 7, 8. So here is a point, 2, 8 is a point. Okay. So my graph would look like this. And then same thing on this side here. Okay. Now, here, if this is x cubed, this here will be 1, and this point here will be 8. Okay. This here is the point 1, 1. This here is the point 2, 8. Now, if I pick a value here, a value between some x value between 1 and 2, okay? Now, notice that when x is equal to 1, y is equal to 1. okay? And when x is equal to 2, y is equal to 8. So if we choose, okay, if we pick a value between here, okay, if we choose a value between x equal 1 and x equal 2, then that value will, that y value will be between y equals 1 and y equals 8. That's what we're saying. Okay. So, and that makes sense because if we pick a value here, that value will be up here, which is between 1 and 8. So we'll talk more about the intermediate value theorem, okay? And this will help us to figure out where there are zeros between functions when it's not some rational number. Okay? So as always, you want to practice as many examples as possible. Okay. So please practice, practice, practice.